Hey, what's up, guys? Okay, so in this video that I'm gonna to use give an alternative proof that Z mod PZ is cyclic. Let's say P is R prime. Okay. So there's the quick proof as I mentioned that one can show that if F is a field, it's a finite field, and you take the multiplicative group, then will be cyclic. If you note this thing that you just set F to be Z mod PZ, then you get it. Okay, so this is like fair the algebra proof. If you know the undergraduate algebra, then the proof is simple. You can check out my our previous videos. Okay, but in this so we have a more elementary way, right? So we have like elementary proof using the Euler phi function. Actually, all this can be made elementary, but it depends on what contents you think is elementary. Okay, and so what we need to use is that suppose you know the so-called Euler phi function identities. Basically, this you take all the factor of n, and you take phi of d that equals to n. Okay, maybe I do simple example. Let's say n is 6, so phi of 1, 2, 3, 6. So this is 1, right? Sorry, 0. It's 1 or 0. Let me see. Should be 1. And the 2 is 1, right? 2 is p minus 1, right? So it's 2. 6 is the number which co-prime to 6 is only less than or equal to 6 is only 5 and 1. So it's 2. So total is 6. Okay. So if you know this identity, then this identity actually indicates one can show this is what we're going to show. If this is true, then PZ mod PZ multiplicative group is cyclic. So what I want to show is the following. This is true. So there's a primitive roots if this is so this is what we're gonna prove. This implies this. Okay, so let's write down a proof. So this proof is like very elementary. So I can that order of P of X to be the order of X. So it's the minimum order such that minimum power that the X to the that power equals to 1 mod P. Okay. So if I take this, right, so I can define so let's say let's call uh let me just write down the so it's let me just a minimum Y 1 such that X to the Y 1 mod P. And I can define a set called BD, where is the X belongs to Z mod PZ, and the order of PX is D. Okay. And obviously that there's a thing called Euler theorem. Tell me that X to the phi of N is 1 mod P. Sorry, this is P. So actually this is P minus 1. But however I say is that any 5D is also 1 mod D, right? So this is the Euler theorem. So what I know is the following that P minus 1 will be the disjoint union of BD, right? Because each element in X will fall into some BD for some D, right? So and the D must divide P minus 1. Because X to the P minus 1 is always 1 mod P. So the highest order is P minus 1. And any factor of P minus 1 may or may not be the order, right? So P minus 1 is this. P minus 1 is this. Okay. So P minus 1 equals to the disjoint union of BD. Okay, so we want to claim the following. If this group is cyclic, meaning that okay, sorry, let me just write down. If this group is cyclic, meaning that this B of P minus 1 is non-zero, right? So it's not empty. Okay. So now we can just see, right? So this is what we got to prove. If it's cyclic, that means that we only need to show that BP minus 1 is not empty. Okay, so now we use the probably the most powerful and elementary tool in the mathematics, counting arguments. Okay, so we just count the right-hand side and the left-hand side. Okay, so we have P minus 1. Sorry, it's the I find that I did a stupid thing. This is a set, right? So I should use the mod PC. Okay, so I just count the number of elements, right? So it's P minus 1 equals to the sum of BD. D divides P minus 1. Notice the following. Notice that the number of BD will just be 5D. Okay, so you need to think a little bit. But actually, hopefully it's not difficult to see. So the number of BD is 5D. The reason is that so you are dealing with the order which is XD. If there's a non-trivial factor of if there's a non-trivial factor from number not corresponding to D, then that element will not in this BD. So the number of the number of the element in the set of BD is just 5D. If you notice this thing, right? Then this formula will just tell you that we already have this formula, right? So if you combine you combine these two, and then you let n equals to P minus 1, and you know BD is 5D. Then what you find is that the BD, in order for these two to match, okay, maybe this is too fast. Let me just do this. So we have these two identity, right? We have these two identity. So it's not sure that up to this stage, it's not sure that the BD is 0 or not, right? So from this equation, so we may have BD is 0, 0, or BD is non-zero, right? Because there may be some order which is empty. But if BD is non-zero, then the number of BD, as I just explained, should be at least 5D, right? So that means that in order for this equation to match, each BD need to be non-zero. Otherwise, that there's not enough BD. There's not enough for right-hand side to match the left-hand side. So each BD must be non-empty for every D. So this shows that B of P minus 1 is actually non-zero. And it immediately shows that there are 5 of P minus 1 and primitive roots. In Z bot PC. Okay, so this finish your proof. So basically the idea is that you just use this formula, just do a counting. Then immediately show this is the result. Okay, so I think we already spent a lot of time. So the next video that we are trying to show this is cyclic for P greater or equal to 2. So this is our goal. And once we doing this, then we almost finish the primitive roots theory. Okay, see you guys next videos.